Today's session is how to think like a simulation engineer. My name is Michael Kalin. I'm a finite element analysis application engineer for the VAR CAD Edge, headquartered out of Marlborough, Massachusetts. And today the goal is to try to educate you on how to think like a simulation engineer for a variety of simulations and otherwise plan out how you're going to do a simulation before you start jumping in there, and mostly tips and tricks on how simulation engineers, people that only do simulations like myself, get around difficult simulations or otherwise think and just view their models. So a little bit about myself. I said my name is Michael Kalin. I have a Bachelor in Science Mechanical Engineering from Wentworth Institute of Technology in Boston. I'm a certified expert, simulation instructor, simulation specialist, pretty much every simulation certification that you can grab I've got. And I've been using SOLIDWORKS for over a decade and simulation for over 5 years. I've been at my current job at CAD Edge teaching troubleshooting and developing simulation for 4 years. And I come from the automation, high-speed machining, and engineering consultation industries. And I like to start off with just a couple of my hobbies. These are called limbic techniques, so that you'll remember this beyond just the content. My hobbies include traditional archery. That's my old bow, which I bought used, and it was a 70-pound recurve, which is way too much bow for anybody. So I had it tuned down to about 45 pound. I enjoy mountain hiking. That's me and my dad on Mount Monadnock in New Hampshire. And I enjoy playing shogi, which nobody knows what it is. Show of hands, who knows what shogi is? Oh, wow. 3 people, 4 people. That's 400% what it was last year. Shogi is Japanese chess. It's a slightly more advanced version of it. And if you have any questions about it, come and ask me. But I guarantee you're going to remember this presentation now. Or you're going to see me in the hallway and be like, oh, look at that weird kid that plays that game nobody's heard of. And I enjoy building 3D printers. That's my mini console that I built on my desk, which apparently at the time, I don't even remember, was clean. Now you can't even see that desk. It's just covered in tools and prints and other various things. So I guess my supervisor was right. I should clean it. But I'll get to that eventually. And of course, making bulleted lists. I'm a level 99 paladin at that. Let me tell you, I can make a bulleted list like there's no tomorrow. So I'm just going to start off with this little tangent here. Simulation engineers kind of get a bad rap as being wizards and just like dark magicians, people that don't know the software. And of course, we think of ourselves as just the geniuses of the company. I can do that simulation, no problem. I'm just Geordie on the Enterprise, just making warp speed. And then what we actually do is just sit around watching that ticker go. Here we go, genius at work. Hopefully by the end of this presentation you'll be able to watch that ticker for a little bit less time because you'll be more efficient. That's really the goal. So let's go over these stages of a simulation. The stages of a simulation are as follows. Firstly, you got to get the model, obviously, and that refers to the CAD model, which I differentiate from the FEA model. And the CAD model, first off, it has to be proper geometry, meaning that you can't have like import errors. It has to be a solid. It can't be like an STL or a shell model of any kind. You have to have solid geometry. And then what you want to do is get the parameters of your study, whatever kind of test you're trying to do. Once you have those two things, you want to use them in conjunction with each other to plan out your execution, plan your method of attack. So if you have something that's like a thermal model and you have very thin surfaces, you have to make sure that your plan doesn't involve using shells because that won't work with thermal. And vice versa, if you do have a large model with a lot of thin faces with static or frequency, you want to start to consider what's the most efficient way that I can shell this or take away dimensions and otherwise simplify it. But I like to execute, or I like to stress that you should plan before you start going into creating the FEA model. Make sure to know what you're going into and what your end result is. Know what your end result is going to be or what you want to get so you can make that roadmap. And once you do that, then you can start making the FEA model so that you can make any adjustments that you need to do. Obviously, not every model that's in CAD is going to work with FEA. There are limitations, and also there's bad modeling practices. So we'll have to get around those in some way. Once you've done that, you want to start executing your plan, setting up your boundary conditions, and then you want to start testing methods of execution, which means actually running a simulation. And during that phase of testing execution, it's very possible that your simulations will fail. And a lot of people look at that as a negative to simulation and say, oh, simulation always fails. I hate it. I'm never going to touch it again. But you shouldn't think of it like that. Really, simulations failing is no different than a sketch failing. Like, okay, show of hands, how many people have made a sketch, modified it, and all of a sudden it's broken? Show of hands. Be honest. Okay, that's really no different than your simulation all of a sudden failing because you changed something or you didn't do anything. It's really analogous to that. It's not that the simulation's laughing at you or just not working properly or is sentient. I mean, I guess I'm still testing that theory that simulations are sentient and just like to punish us. But until that theory is found to be sound, otherwise, just think of execution as the phase when you're drawing everything and testing it, and not so much that you want to immediately hit that run button and boom, pop, magically you've got the result and it's 100% correct. Remember, simulation is a process, and processes have stages. So once you do test your method of execution, you've got your simulation results, then you want to go into post-processing and look over them and then verify them. And when I say verify, that's actually a multi-stage process. There are virtual verification tools inside simulation, but also ultimately verifying means building a prototype and testing it, because simulation is never meant to replace prototyping, it's just supposed to enhance it. Such as instead of building 8 prototypes that fail and 1 that works, you can test 8 virtual prototypes and see that they would fail before building them, and then build your final prototype and make sure it works immediately. But you still really want to test that prototype in real world just to get peace of mind. Okay, so I'm going to go over 6 tools of the trade, and then we're going to go through examples on how to use those tools and what exactly they are. So the 6 tools that we have, or what I like to call them, are the chainsaw, virtual reality, transmogrifier, the reverse 3D glasses, the doctor, and the Jedi mind trick. So let me go over those in detail. Firstly, we have the chainsaw. Chainsaw means cut your models in half. When? Pretty much always. Now there is an asterisk next to that because some studies like frequency and vibration, you shouldn't use symmetry, and we'll see an example of why. But otherwise, why would you not? I'm asking you right now, would you like half the solve time or all the solve time? And people who say, I don't like using symmetry, you're saying, I'll take all the solve time, please. Just all of it. Why would you do that? You can cut it in half any time, use symmetry, and you'll get the same result. So really, you should always use the chainsaw. Next is the virtual reality. So many things can be made virtual in simulation, and I'm not talking like virtual stress. I'm talking taking out a solid part and replacing it with a virtual component, such as bolts or virtual masses. And the advantage there is you don't have to mesh it. It's just, boom, it's gone, but it's still represented the same. A good example of this is if you're designing like an engine mount. You don't want to mesh the engine, that's really complicated geometry, but you want the weight of that engine, so you can represent the weight of it virtually without having to mesh and run it, and you'll get the same result as if you did mesh and run it with the material. And another big advantage is that you don't need to interfere with geometry. That especially applies to bolts and pins, because usually pins are press fit, and you build a model press fit, but then when you put them together virtually, you have interference, and interference will always fail. This picture, by the way, is from SOLIDWORKS headquarters in Waltham. That's their virtual reality machine. It's like their little holodeck. You walk around with 3D glasses on that track your head movement, and it renders everything so it looks like you're in 3D. It's pretty cool. If you can ever check it out in Waltham, if you're ever in the area, I'd recommend it. All right, next up is transmogrifier. So this means changing a model. So if a model doesn't want to work for FEA, make it work through any means necessary. FEA configurations, change in geometry, good old-fashioned elbow grease. Just whatever means necessary. And a lot of people cringe when I say this because they say, then I'm going to start changing our production models, and then people are going to manufacture it wrong, and I'll have like a which is which situation, and then I'll have to save it out as like FEA 1, 2, 3. No, you don't have to do that. Just make FEA configurations and everything will be hunky-dory. Whether you use PDM or you save over a network like you shouldn't be, everything will be fine as long as you keep track of your configurations. And I'll show you an example of how to do that. It's really not as complicated as you think. Next up, we've got the reverse 3D glasses. So when you can get rid of dimensions, you really should, because it's going back to that question, would you like more solve time or less? So that means taking away dimensions like solids to shells, going from 3D to 2D, or weldments to beams, going from 3D to 1D. And it also means using 2D simplification whenever possible. Show of hands, how many people know what 2D simplification is in simulation? Okay, I'm going to educate you on that. 2D simplification is actually added back in 2011, and it's a way of just going back to 2D, even if you have 3D. Now, there are limitations to the reverse 3D glasses, and that is cross-sections have to be constant. So if you're taking something like a wrench and just using a 2D cross-section on it, as long as that wrench doesn't taper or round at the end and the cross-section's constant, then you're fine. But if it does taper or change or draft, then you're only taking one section of that. Sometimes you can get around that. For example, you can just do the weakest part of it and run a simulation, and if it's okay, then the strongest part of it's obviously also okay. But just take into account that reverse 3D glasses are great, but it has to be in appropriate context. Next up is the doctor. Does anyone get this joke? This is a good joke. The doctor inside the TARDIS, come on. There are many tools to analyze the healthiness of a mesh. There's the mesh check plot, the energy error contact visualization, and when all else fails, there's troubleshooting. I like to use what's called the pyramid method, and I went over that 2 years ago at SOLIDWORKS World when I did a presentation called How to Troubleshoot Simulations. So I'd recommend checking that out. It's archived on the SOLIDWORKS World website. It's back in 2014. You can just also search my name, and you'll find all my presentations. I've presented every year for the last 3 years. So the doctor is a way to check the healthiness of the study, and there are a variety of different definitions of healthy. For example, there's healthy mesh versus healthy stress versus healthy displacements, and we'll take a look at all those examples. And last but not least, we have the Jedi mind trick, which uses virtual forces and displacements as opposed to using complicated assemblies. So instead of using every single part of an assembly, if you have like no penetration contact between two parts, instead of having those parts transfer forces through each other, you can just put a virtual force that represents that and otherwise simplify it. So I call this a Jedi mind trick because it's like telekinesis. And before you email me, I'm aware that that's not actually the Jedi mind trick at all, but I couldn't think of a snappier name. I mean, I could call it like force move object, but that's lame. Jedi mind trick is just cool. So we're going to call it Jedi mind trick. Any objections? Good. Moving on. Okay, so now we're going to go into examples of our tools. We have these 6 icons right here. I've got this little 8-bit chainsaw with the blue screen effect that didn't work, so I just left it. I've got Calvin and a transmogrifier. I've got the reverse 3D glasses. Does anyone know what the bottom right one is?
Virtual Boy.
Virtual Boy, thank you. I've shown this to like 3 people and they didn't know what it was, and I was just depressed. And then we got Master Yoda for Jedi mind trick, and we've got the TARDIS for the Doctor. So now let's go into some examples. Firstly, we've got this simple plate example. We're going to start off simple, but it's going to get more complicated, trust me. So in this simple plate, I'm just holding it on the 2 bolt faces on the left, and I'm stretching it on 2 bolt faces on the right. And in reality, there are bolts in those holes. 2 of them are being held, and the other 2 have another plate attached to them that's being torn in tension. Like a simple tension test where you have 2 plates sandwiched between another. And in this case, I'm going to take advantage of the chainsaw, the Doctor, the Jedi mind trick, and reverse 3D glasses. So let's go to SOLIDWORKS. Shrink this down. Windows. Oh, it's showing up there, but it's not showing up for me. That's weird. Hold on, let me just cancel out of this. PowerPoint, people, you gotta love it. Technical difficulties. Okay, cancel out of that. So it works. Now wait for the video to come back. If it comes back. You gotta love this, right? I'm using this multi-physics solver to do all this complicated stuff, and it works fine, no problems. But then connecting to the HDMI in the PowerPoint, oh boy, you're in for a world of hurt, let me tell you. Let me try resetting that connection. Boy, this is anticlimactic, huh? Is there a tech support guy in the house? Anywhere? They abandoned me in my time of need? All right, let me try this. Let me try projecting only to the projector itself. If anyone could like run out there and get someone from SolidWorks, I'd like really appreciate that. Hey, there's SolidWorks. Okay. I think. The aspect ratio is rather poor. No, don't do that now. Yeah, it's okay. You just turn on Task Manager and threaten to delete it, and then it comes back usually. Oh boy. Okay. Now I have a contingency plan. I did record this presentation just in case, and it doesn't want to even display. I am batting 1,000 right now. Okay. Everyone, use your imaginations real quick. We're all just going to imagine that everything's working properly and everything's fine. Performance. All right, try ending it and they'll just bring it back. Now I'm like craning my neck to look at the screen because my screen's not even duplicating. Open up SolidWorks. Now I got to really bump up the speed I'm doing it. All right, it's back. Open recent. One of these here. There we go. Yeah, just hold a mirror for me, that'd be great. I seem to have lost duplication. I'm not sure what happened, so I'm just gonna run with it. This aspect ratio is rather low. Any second now. Boy, I'm really tempting the simulation gods. All right. Okay, back up. That's right. What did we say to simulation gods? Not today. So here is my simple plate right here. And let me activate my configuration. And let me shrink this over. Okay, so here is my simple plate. And like I said, ordinarily it has 4 bolts. 2 of them are restraining it, 2 of them are pulling it apart. So using my Jedi mind trick, I can instead just use a force to pull it apart and a fixture. So that's what I did right here, is that I have a force on 2 of my bolts, or 2 of my bolt holes, and I have a fixture. And this is run as a solid part. So if I check my mesh right here, show my mesh, you can see this is a very low quality study. So it's just an average amount of mesh on here. And from that, I can get a stress result. So my stress result right here shows that it's a little bit above yield. If I right click though, and I say to ISO clip it, and I set that to something high, like close to yield, you can see that that's actually just a small percentage. and it's not quite across the thickness, so I probably shouldn't worry about it too much. That happens a lot when you have low-quality small elements. The reason is because they're not full triangles in the area of the simulation stress, so they're taking overestimations. And also, because they're so small or so stretched, they can't properly render for that area because there's only so many of them. It's akin to like looking at an 8-bit drawing and trying to get detail out of it. There's not enough pixels in there to display it. So think of the nodes and elements like pixels. The more of them, the more refreshing the image, and thus the more clear where the stress is. So this is a solid version, low quality. And if I look at my mesh, if I, for example, go to my details right here, I can see just how many nodes there are and how long it took to solve and how much percent above or below a certain ratio. So for aspect ratio, we like to say that everything should be 1, which means that all triangles are even. They're actually tetrahedrons, but they look like triangles because you're only looking at it on the surface. So that means that the base, the height, and the width should all be equal. Not necessarily it should be 1 millimeter, it should just be, if it's 7 millimeters, it should be 7 in all directions. So it's saying that percent less than 3 is 99.5 and over 10 is 0. So that actually sounds really good, right? And I only have 4,000 nodes. But it didn't look really that refined. So if I do a high quality version of it, just duplicate it and change it, show my mesh. Now you can see it's very dense. And if I go to my mesh right here and say details, now I'm at like 99.7%, but I've jumped up to over 10,000 nodes. Now I've gone from like 4,000 to hundreds of thousands. That seems like a very big increase for not a lot of gain, only 0.2%. But actually, it is a lot of gain if we look at the overall healthiness. So let's go back to the low quality. And if I look at my mesh quality plot, which you can get by right-clicking and say mesh quality plot, if I click on that, I have it set right now to 3 to 1. So everything blue is 1, everything green is 2, and everything red is 3 or above. And you can see a lot of red elements near the holes, and it's overall kind of 2-ish, not mostly 1. And so I don't really have a good aspect ratio overall. I just have an average aspect ratio, which is fine for most cases. And this is a good ratio to use for your initial study when you're just playing around with it, making sure everything looks hunky-dory. You don't want to immediately jump into high quality because you'll just jump into long solve times. Now, another thing you can do to look at your overall accuracy is right-click and create a stress plot and say energy norm error. So energy norm error is overall differences in the calculations because this is all an iterative process. So iterations have percent error that's allowable, and this is saying how much percent error was calculated. So if I click over here, here's my scale, and I'm at something like 15 to 25% in some areas, and 15% is pretty high. We like to keep it under 10%. 5%, 0% would be great, but it's never going to happen. So 1 to 10% is where you want to really lie in this area. And notice where the error is. It's right on where your holes are, and that's also where our high stress was. So can we really trust that stress? Not really, because the energy norm error is very high there, so that means that the allowable percent error is high. So if we go to our high quality version, and now we look at our results, and let's do another stress plot, and let's do energy norm error. Now it looks great. Now there's like no red areas, and I can shrink it down to something like 10% or less, and all that energy norm error has gone away. As a consequence, if I now go to my stress plot, and I right-click and I do the ISO clipping, and I again set it to something close to yield, here's that same setting. Notice now that it's all the way through that hole. And it's not really serious because it's not going like from the hole to the side, but that could still lead to serious fatigue error. Whereas before it looked like a tiny sliver, now it's a clear half cylinder. Question?
Are you applying a force in one direction to the entire cylindrical face of the hole?
Yes, we are applying a force to the face of the hole, just like a bearing force that the bolts would apply. Well, are you saying like both front and back?
The entire circumference.
No, oh, no, it's only the front face, as if it was like a bolt pulling on it. Yeah.
I couldn't tell from the visualization.
Yeah. Okay, so that's the effect of using your doctor to look at your overall healthiness. Check your mesh healthiness, then check your energy norm error, and make sure everything's hunky-dory. I think a lot of users don't even know that those tools exist, but they are there to help you. And now I can take advantage of even more simplification from this. I've already taken away the bolts, but another thing I can do is take away the thickness. So if I can instead switch it to a shell version, so if I now show my mesh here, show my mesh. Where's my show mesh? Sorry, let me just create a new mesh, it's no problem. Okay, so here's my shell mesh. So all I did was click on the solid body and switch it from a solid to a shell by selecting the face and giving it the overall thickness. It's not that the shell is just that very thin body. It's still representing the overall thickness, 10 millimeter thick plate, except now it's doing that virtually, and I only have to mesh this thin plate 2D with triangles as opposed to tetrahedrons. So the solid and the high quality versus low quality, something like difference of like 30 seconds versus 6 seconds for solve time. But now if I run this with the very low quality with the shell, this one, boom, I can't even see that come up. It's like less than 1 second. And notice that I get a pretty similar stress result there. But just like before, I can check my mesh healthiness. So I can show my mesh healthiness, and I can see it. The aspect ratio, again, near the holes, because you're going from a straight mesh to a curved, is kind of skewed. And also, just like before, I can right-click on my stress plot, and I can go to energy norm error, and look at how much energy error I'm getting near the holes. And again, I'm getting something like 15 to 20% in those areas. So I can instead switch to a high quality. So again, just duplicated it, switched to high quality. And now if I look at my stress plot, notice that this one's back in 3D, right? It's because I edited the options and said render back in 3D. So now I can look at my stress. It's pretty much exactly the same as what the solid got. And now if I look at, again, stress plot, energy norm error, now my energy norm error is pretty much gone thanks to my high quality. And if I check my overall details on this, solver messages, solve time, only a couple of seconds. So the difference between high quality solid was something like 6 seconds versus 30 seconds, so a huge increase. And the difference between the shell high quality, low quality was practically nothing. But I'm not done, because I can also take advantage of symmetry in this case, right? By just making a configuration. So if I just switch to a configuration version, so I just made an FEA configuration, inserted a cut there. Question?
Yeah, just really quickly on the energy norm error.
Yep.
I saw the high density version, it looked like the energy norm error was actually higher, but it was more concentrated to the whole. So you're looking at the...
Well, it may have looked higher. That's probably just because of scale. Because the energy norm error was showing like 1 to like 45%, as opposed to 1 to 15%. Yeah, you always got to be concerned about that scale on the side, because it can show you something that maybe look like it's higher, but it's actually just because it's scaled up, so it's actually better. Okay, so now I've just taken advantage of symmetry. So the only thing I've done is make an FEA configuration, cut it in half, and I added a symmetry condition. Except there's also this one very important safety tip, that when you do symmetry and you have force, you want to make sure you cut your force in half, because now you only have half the body. That's not important for pressure, because that's based on unit area. And also, if I had selected this based on per item instead of total, then that also would self-correct, because it's per item, how much force per hole. There's one hole versus 2 holes. But just take that into account. When you use symmetry, you probably need to use half the force. So now I can actually extrapolate that back to my full model. So now I have a shell version, half of it, and I have practically no solve time, whereas before I had something like 6 to 30 seconds, so a rather large increase in gain. All right. And go back to my slides here. I'm not even going to go full screen after that fiasco. Okay. So now let's go to another example, this time using a simple assembly. We're going to use this table assembly, and we're going to again use the chainsaw, the doctor, the reverse 3D glasses, and a Jedi mind trick. Notice it's the same that was used before. So now if I go up here and open my recent, boy, it's really hard to read this. Open a recent. I want everyone in this review to say, he did a great job just reading it on his screen because his screen died in the middle of the presentation. Very adaptable applications engineer. Okay. So here is this table. Now I like this example because a lot of you are probably looking at it saying, okay, it's a table. I'm just going to run that solid. Big deal. It's simple, right? Wrong. You always should be using these tools because why wouldn't you? Yes, it is possible to run this as just a solid. So all solid, why not? Here's our stress. So we have just 4 legs fixed at the bottom, and we have a force on top. And I use a force here because it's easier than adding a bunch of items on top with weight or like splitting the lines. But you can do that if you want. You can split lines and put distributed forces to more accurately represent maybe there's a heavy desktop on the left and there's like a light laptop on the right. In this case, I'm just using like maximum amount of force. This is like a worst case scenario applying that force. But here we have our stress result for our solid. But if we go to our energy norm error right here, and I set this to something reasonable, let's say 10%. Oh my God, there's energy norm error above 10% all over, especially in those corners. And a lot of it has to do with the mesh itself. So if I go to my mesh healthiness and show that, you can see that there's just a lot of bad elements across the thickness because you're trying to mesh something that's relatively thin with a large span using solid elements. So why wouldn't you use that as a shell? So let me go to my proper method right here. What I would do, since I think like a simulation engineer, I look at that and say that table's constant cross-section, shell it. Those legs are constant cross-section, make them beams. And you're probably saying, why would you make them beams? They're made of wood, they're not made of iron. Well, metal beams are not everything that beams are meant to be. They can be really anything that's just constant cross-section over a long span that you only care about one dimension, length. And they will represent their own inertial cross-section just fine. And it's easy to do this. You just right-click and say, treat it as beam, and that's it. And then once you have your joint cross-sections or your joint group, I just put in contact sets to bond those table legs, because they're beams, to the shell. So then it acts just fine like a solid-to-solid contact condition. So now if I go to my stress result, here's my stress. Notice that the beams are gone. And that's because you generally look at beam stress as something like axial versus looking at stress for a solid or shell as von Mises. But at any time you can just make a new stress plot. So new stress plot and just say I want to look at beams. And let's say look at axial stress. So there is your beams right there. You can look at displacements all at once because a millimeter is a millimeter no matter what. So that's a fair game. And if we do a comparison right here, if we go back to our solid displacements, the maximum displacement is something like 6 millimeters. But then if we go to the shell version, it's something like 7.5, 7.25. So it really increased. And that's as a result of that increase in accuracy because I now have a very refined mesh thanks to the fact that it's 2D. But you know, I can go even further with this. Just might as well take out that chainsaw, right, and cut it in half. Well, actually, I can go one further. I can cut it into a quarter because I can assume that the length is the same as the width because I'm using even distributed force. See, that's why I did that. It all comes back. If you did have different forces on the left and right, then yeah, you can't get away with that. But any amount of symmetry you can use, you might as well use it. And this is no different than using it on a part. You see, I just put symmetry constraint on the edge for that shell. And I now only have one bonding condition for one leg. And again, I shrink my force down. Now if I go to my displacements, my maximum displacement is something like 7. which is interesting because it went from 6 to 7.5 to 7, so it almost like balanced out as an average right there. And this is my most refined version. So that's an important lesson to learn is that convergence can sometimes teeter-totter. You can go up and you can go down, but the main point to remember is it's not converged until it stops moving and you get an accurate response. Okay, let's look at a pure weldment example. Now in this case, notice that I took away the chainsaw, and I'll go into why I did that once I get in there. So now let me open that up, open recent. Good thing they put this preview in, right? Thank you, SOLIDWORKS engineers, otherwise I'd be totally lost. So here is I say it's a pure weldment, but it actually is a mixed meshing because it has a mixture of solids and shells. We have these little gussets in here, and we also obviously have a bunch of weldment beams. So I'm going to weld those beams together, but I'm also going to virtually weld those gussets on. And since they are constant thickness, I'm just going to make them as shells. Why bother making them solids? So that's what I've done, is that all of my parts here in my study are simplified. So I have all of my beams, and I have all of my shells. And whenever you do mixed meshing, you always have to define it, because otherwise they don't talk to each other with a contact set. So I've just put all of my contact sets in, and that is a little bit of a tedious process. So for that, what I like to do, if you hover over them and just shift select them, you can see all of them. There's also a contact visualization plot where you can actually have it highlighted on the screen. But what I like to do is what it's called the pyramid method. What I did when I built this is I didn't start with this model. I started with this, the first level, made sure everything was running correctly with just a force, maybe just self-weight gravity. Everything was working well, added the second layer. Everything was working well, added the final layer. So why bother going to the top level? Because that just means you have that many more potential problems. Because you can misclick, you can forget one contact set, you can put a force in incorrectly. It's easy when you're doing it over and over and over again, fat fingering it, to make those kind of mistakes. So it's better to work your way slowly. Rome wasn't built in a day. Don't build your simulations like that either. And that's especially good for troubleshooting too. Just start from the bottom, work your way up. Eventually you'll find that one problematic part of it. Okay, so in this case we have multiple forces. We have force going down representing the weight of multiple machines on top, and we also have a lateral force on the side to represent wind loading. That's one reason that I might not want to use symmetry, is that I can't use a quarter because I have the wind loading on one side, but I might be able to divide it in half. The reason you don't want to do that is that I can get a displacement result and a stress result from this no problem. But because there are machine elements on this, I need to run a frequency analysis to make sure that those machines are not going to vibrate this thing to death. So that's easy enough to do. I just go down here to my frequency study, and I just copy everything over. Just click and drag all of your forces, your fixtures, your definitions, because static and frequency talk to each other, no problem. And from here I can get an amplitude study. So if I go to one of these more severe amplitudes, you can notice if I animate that, there's no way this is symmetrical, right? If I were to cut that in half, because it crosses the line of symmetry. So that's why you don't want to use symmetry in the case of things frequency, buckling, or dynamics. And now if I want, I can right click and say list resonant frequencies. And I can see which frequencies that I want to avoid here. So all of these frequencies, if the machines do operate in that range, the thing's going to start getting a wicked shimmy. And that's what I want to ultimately avoid. Okay. Now let's look at a nonlinear example. I'm going to look at this cell phone screen right here and see if I can predict how much damage it's going to get from an impact. And in this case, we're again going to use the chainsaw, the doctor. The doctor's going to be a little bit different because we're nonlinear. The force, telekinesis, Jedi mind trick, and reverse 3D glasses. Reverse 3D glasses are very important for this one because I'm dealing with a very thin screen. So I don't want to really run that as a solid. That's just a death sentence. Load this up. And let me go to my original configuration. Okay, so here is my cell phone screen with a simple weight on top. Notice that this is heavily simplified. I don't have the phone and I don't have some like complicated looking weight. It's just a cylinder with a dome on it. That's the name of the game. Try to keep it as simple as possible. Yes, there are more catastrophic cases that this phone may have to encounter. And yes, the phone itself has to absorb impact. But you know what? You can do those as separate studies. You don't have to do everything at once. Sometimes doing it piecewise is the better option. So this is one piecewise part of this design. Can this screen withstand a weight being applied at a speed? So in this case, I have a variety of nonlinear studies down here because I use it with a variety of different materials. So if I go to my solid, von Mises, I use a von Mises glass for this so I can see if it's going to ultimately crack. Because if you use a linear, then it's never going to crack. You know, you can apply the weight on and off forever, and it will always return back to zero. But if you look at a von Mises glass, which you can get a lot of materials from Materiality, which is built into SOLIDWORKS, you can look and see when it crosses that threshold. And if it does cross, if there's residual displacements, then that glass is gone. It's cracked. It won't actually show it like cracking and breaking because who cares what it looks like? You just care yes or no. Is it safe? So for the setup on this one, I have a fixture for the outside of the glass, and I have reference geometry controlling my weight. And I use a time curve for my reference geometry. So if I go down here, I have a time curve. So it's going to go on and then off. It's going to press upon it and then leave, just like a weight dropping on it or ultimately a force pushing upon it. So ultimately, I don't really know how much force is going to be applied. But this is like a standard test that they do in a facility for testing glass screens, is that they just put a linear actuator on it with a certain amount of displacement and push on it. And they keep pushing it more and more and more until it breaks. So they don't really measure how much force. They're looking for how much difference in displacement is going to ultimately crack it. So that's what we're replicating here without having to actually make this glass. And obviously no penetration between the weight and the glass itself. So now if I go to my stress result right here, it looks like zero stress, right? That's because I'm at time step 2, which means I've fully removed the weight. So obviously there's no stress there. But if I edit definition on this, I can just go time step 1. So this is when it's fully as maximum displacement. So that's the maximum amount of stress that you're going to get from this. You can see the effect on the bottom of the glass right there. And what I'm really concerned about is displacement. So if I go to displacement number 2, or time step 2, you can see that there is not a whole lot of displacement here. Let me make sure I'm on time step 2. Yep. So that's the end of the simulation when it's removed itself. And you see the glass is all blue, which means 0. So that looks good, right? But let's look at the mesh healthiness plot right here. Show it. Oh, that's garbage. It's like all 25% or higher for 15 or higher for a mesh quality plot. The aspect ratio is terrible because the glass is so thin. Trying to mesh it with solids is really haphazard. So instead, let's try the same one, but instead we're going to try it with shells. And you know, while I'm at it, I might as well also take advantage of symmetry, right? Because I got half a screen, why not? So I've put symmetry on it, and I've changed it so it's now a shell on the bottom for the glass. So now if I look at my mesh healthiness plot, mesh quality plot, now it looks much improved over that last one. Now with nonlinear, unfortunately, you don't have the option of doing the energy norm error. The reason is that every single time step in nonlinear is another calculation, and it has to recalculate the stiffness matrix constantly. So unfortunately, we don't have access to that kind of information. Instead, what you probably want to look for is things like contact pressure and overall symmetry of your displacement and stress results. If you have what should be a symmetrical stress result and you have something that's way off, then you probably want to enhance that mesh in an area or two. So and now if I look at my displacement results in edit definition, 2 seconds. So now I'm at 2 seconds, and look at this. There is a residual displacement. It is very small. It's only 2 to the negative 2. But very small displacements like that in glass lead to big problems. This glass is cracked. because that's a residual displacement after you've left. Elvis has left the building up here. You can see the weight's no longer applied to it. So that glass has officially failed. So that's the difference between using a solid versus a shell for something that's very, very sensitive, like a von Mises glass. You'd think it won't make that much of a difference, but it really does. And I can go one step further to simplify this by replacing the solid entity of the weight with a force, using my Jedi mind trick again. So I've already taken away the 2D or 3D to 2D. But another thing I can do is I can right-click and say list result force. No, not use beam forces. List result force. I really need glasses over here. Thank you, thank you. So I can list result forces and look at contact force, and then click on this face right here and say update, and then say over time, and it'll give me my force over time. So now I can apply that curve to the face and then eliminate another body entirely. The only trick is that you have to apply it to the correct geometry. So I'd have to put a split line and represent that. So that's what I've done right here in my final study, Jedi mind trick. So if I activate that configuration, so the body's gone, I put a split right there. And if I look at my displacement results, I've got the same result here, but now I have a faster solve time because now I have less bodies. Because the thing about using bodies to interact with other bodies is it has to calculate for every node. And that means every single node on that weight. You can try to get around that. Like I have a big bullet shape. I really only need the bottom surface, so I could probably cut it down. But even still, the most calculation time is spent on contact between other bodies, reaction forces, action and reaction. So if you can get around that by using a Jedi mind trick, you really should do it because it's beneficial to you. And you'll get the same result as long as you have the accurate inputs. So I like to tell people you should probably use this Jedi mind trick study for iterations, so you're not sitting there waiting and waiting. And then once you're confident in your design, you're confident in your parameters, switch to the more accurate body-to-body method because you'll get more information out of it. You'll get more peace of mind that it's the accurate. Question?
How did you arrive at the right contact size for your split surface?
For the contact size, I actually made a deformed body of the weight when it squashes it and then measured it. Yeah, so everyone knows that at any time you can right-click and say create deformed body from study. So that's what I did to get that size. Is I just looked at how much the weight squishes and deforms, and I just used that area. But keep in mind, it's always going to be slightly inaccurate because that area is changing constantly, and your split line is not. So it's an approximation. Okay, let's look at another example. This time using this turbine for solids and shells. Has anyone gone through the simulation training? You might remember this file. But in this case, I'm also going to do a vibration study on it. Just open this up right here. There it is. So this is a good example because it looks like you can use symmetry on it. However, you have to use cyclical symmetry because you can't just take like a quarter section of it, because if you did, you'd be cutting some of the blades. You have to use what's called periodicity, where you have even surfaces between those blades. So you're cutting out just one section, like 1/16 of it. And if you had 16 of those like Legos and you put them together, then you get the entire shape. We have to do that because of the complex geometry of it crossing over its own plane of symmetry constantly, but it definitely is possible. However, I didn't put in the chainsaw in this example, and the reason for that is, yeah, I can get a static result out of this by putting a centrifugal force, no problem. But because it's a turbine blade, I probably also have to take into account its frequency, and if you were to do a frequency study down here, in this case, this is your vibration. So if you do like an amplitude study, if you right-click and you do your frequencies, you're going to get different frequencies if you used your periodicity model versus the full model. but it's going to look perfectly accurate. That's the thing. I really think SOLIDWORKS simulations should probably just say, you selected symmetry for a frequency study, what are you doing? That's not a good idea. But it does give you the option to do it for whatever reason. And I'll show you right now an example of how you would transfer it. So if you go to New Study, and I select Static Study, now if I go back to my vibration, I can just Control select everything. So I'll just select all of my bodies, all of my contact sets, which there are many of, my fixture, my loads, my mesh, and just drag and drop that. So notice I got that little arrow indicating that everything's okay. Drag and drop. Now I've got the complete static study set up one-to-one exactly like my frequency study, so I can just run that. And this one runs very quickly because all of those blades are actually just surface models. So we just put in our thickness and then we bond them together. Trying to run something like those turbine blades as solids would be really difficult because they're so thin and they're curved. They're very curvilinear geometry. So that's like the bane of all solid geometry. I know I'm kind of like hammering on solid geometry, but solid geometry is there for a reason. I'm just trying to illustrate to you that it's not your only option. Because I just find that a lot of people that struggle with simulation, that have problems and come to me, they're not using mixed meshing when it really benefit them. So that's ultimately my goal today. Okay, I'm going to skip through that one because I wasted so much time. But if you have questions on it, come to me. That one also, the scaffolding is from the training. So let me go to this thread pull test. Actually, do I have that? Yeah, I got that one. Except I didn't open it before, but I know it's in here. Now's the time for questions while I'm opening this up, if you got any. Thread test. Okay. So in this case, I'm going to use 2D simplification to run this thread test. I'm trying to do like a thread pullout. Now, running threads in simulation is always ill-advised for the same reason that modeling threads is ill-advised. There's lots of faces, lots of vertices, lots of edges. So that can increase your mesh complexity pretty quickly. And this is also a good example of using a transmogrifier because here's my original configuration right here, my default. And if I hatch that open, you can see it. This was modeled not one-to-one. The female thread is slightly oversized, and it has fillets that the male thread does not have. So any global bonded condition or global no penetration will not be in effect. And also, it's not really realistic. In real life, they eventually touch one another. The point is that this was modeled just like with mid-tolerances. And so in reality, they do contact each other, but in the CAD world, they don't. So you just want to make sure that you take that into account. So if I make my FEA configuration and see now they're one-to-one, and I've taken away the fillets because that just adds complexity, and really they don't add or remove that much strength. So while I can try running this one as a solid, if I take a look at my mesh right here, this is a very average quality mesh. And if I go to details, I'm talking about hundreds of thousands to tens of thousands of nodes for a basic mesh. You really don't want to run that, especially because you're talking about no penetration contact. And every single one of those faces has to calculate. That gets complicated real quick. So instead, when you make a study, you always have the option of making a 2D study. You just represent it by a cross-section. So that's what this one is right here. You can see I only have that cross-section, but everything else will be extrapolated. And I can show a very simplified mesh, but I can also just crank that way up to a very, very fine mesh. And I can run that with a fine mesh as well as no penetration contact. So if I show my mesh right now, Let me go to the final version where I put mesh controls in. So you can see I put a lot of mesh controls in right where they touch each other. So the result of that, if I go to my original study right here and go to my displacement result, so they're stretching out a little bit, but that is a unibody condition because it's globally bonded. So they're not separating in any way. The teeth aren't going to leave. I mean, if you use Loctite, I guess that's the appropriate response, but in reality, that's not how it goes. Instead, if I use the no penetration, they do separate, but it looks like they separate a lot. That's actually just because of the scale. But if I put it back to a 1-to-1 scale, go to true. So that's how much they move. But you can't, there is some separation in there very slightly. More importantly, if I go to my stress result right here, okay, everything looks hunky-dory, but that's with my average mesh. Now if I go to my enhanced mesh, go to stress, there's actually, if I shrink this down to my yield strength, there are some sections near those teeth that are starting to go above yield, mostly right at the, right here, at the bottom tooth. Keep in mind it's still scaled up, but right at that bottom tooth, some of those sections are above yield, and that means that tooth is going to start to break. Then the second tooth is going to be the first tooth, and it will break, and so on and so forth, cascade failure. So although it's not going to show that cascade failure, that's the result you're going to get from this tear out test, that this bolt is ultimately going to fail. And if you wanted to, you could even do it as like a pie slice 3D and run it as a fatigue study, and it would probably give you an estimation of how long it would take for one of those to crack, and it could predict how long before all the threads go. So that's a great example of using 2D. You pretty much always want to do that with threads, unless you're doing some kind of like virtualization. Okay, so here's the big one. It's the one I want to get through. Hold your question to the end. I want to get through this example because I'm running out of time here. This is an example of a study with a lot of interferences, and I have to use every trick of the trade to try to get this to work. So we use a chainsaw, the TARDIS, the reverse 3D glasses, the virtualization, Jedi mind trick, and the transmogrifier to try to get this to work. So if I open this model up and I do my interference detection, I'm going to see a lot of different interferences for the same reason that the bolts were, because I have mid-tolerance built into all my parts. So if I go to my original right here, and I go to evaluate, I can check interference detection and say calculate. I have a whole bunch. So that's all my interferences. Notice a lot of them are just around like the cylindrical entities. So to get around that, I just made an FEA configuration. So this is where people get hung up. They say, that sounds like a lot of work. I don't want to do it. But it's actually not. And you're really saving yourself a lot of time. By not making FEA configurations and not making simplification, you're just making more work for yourself. I call that the Christopher Columbus theory of laziness. I want to go from here to here, and I'm going here. All the way around the world to get to this very small distance, because you're just making more steps for yourself. So I'm going to step through how exactly I did this. I have an FEA configuration, so here it is. Notice that it's symmetrically cut. The advantage of doing this as an assembly is that I can just put an assembly cut in the assembly and not have to worry about cutting every single one of those parts. Because otherwise you got to put the exact same cut in. Instead, it's much easier to do it as an assembly, and you just have assembly cut right there. Now, every single one of these parts is in a sub-assembly. So you see right here, I got this EPS manifold, alluvial damper. These are all named after sci-fi jokes. I applaud you if you get it, but I won't judge you if you don't. I mean, I judge you a little bit. So open up this one right here. And just like I said, I have default and FEA. So here's my default. And if I again check my evaluate for this part, I can check my interference. I can see that I've got that one interference. So that's what I need to fix. So to do that, I just open one of these parts up and change this to an FEA configuration. In this case, I left this one the same, and I open up this one. The reason I want to use this one is because I also want to take care of those bolt holes. So if I go to my FEA configuration, I've changed those holes by just configuring the dimension of that part to be the correct size so it's line to line with the other part. And then I just put that into my subassembly, So if I go back to my subassembly here, close this. Now I just make sure that in my subassembly for the FEA that I reference that FEA part, and then same thing in the overall. So now I have my subassemblies FEA with parts FEA. That's not really that much of a chore, is it? I just made 6 configurations and changed 2 or 3 dimensions, and that's it. That's all I need to do. And none of my parts are now going to be off because the manufacturing guys get it wrong, because as long as they use a default configuration, which the drawing calls out, everything will be fine. You can change in the FEA configuration to your heart's content. Nothing will be changed or broken. A lot of people are scared about that, and what they end up doing is saving as a copy, like FEA version. Don't do that, because then you're really in a which is which version. Because then somebody makes a change, and you got to change this, and you make like 2 changes, and if you have 3 versions of it, you got to make 3 changes. It gets really complicated. The other thing I need to take into account are the bolts and pins. So notice that now my bolt right here is like ghost blue. It's a virtual bolt. So I went in and in my assembly or my static study here, I just said to remove that, and instead I use a connector and I put in that bolt. And if you use toolbox components, they'll automatically be created. And in fact, they'll even put in the correct torque for that bolt. You have the option of just right clicking and say, make everything connectors for me, and boom, you're done. Super simple. So now I have just those connectors, and I replace the pins with virtual pins. Now there's another advantage of using these virtual connectors in addition to the fact that they don't interfere, and that is at the end you can get information on their shear and their torque and their factor of safety. And you can do things like put in virtual keys and torques. So now if I do this, of my loads by the way are just temperature. So this is like a flexible bellow with a steam on the inside. So I have fixtures on the sides and I have temperature on the inside. So now if I go to my stress result, this looks way, way bad, but it's just because it's scaled up by a lot. But now if I right click, I can say list connector force. So here's all the force of my connectors, and notice one of them comes in green because I put a factor of safety in. So it's saying your factor of safety is A-OK. If it was bad, it would be bright red. The white and gray ones mean I didn't put a factor of safety in, but I can still get their information like shear and torque right there. And you can even save that list out as an Excel list. That's especially important to do because a little known fact is that bolts and connectors in simulation are one of the very few nonlinearities. If you increase the force by a factor of 2, your factor of safety for your bolts will not decrease by a factor of 2. It could do really anything. It depends upon the simulation itself. That's just the nature because they use all these polynomial equations to ascertain their factors of safety. Okay, so here I have this result based on this thermal temperature. But if I use my old friend, the let's press. Let me make a new stress result. If I use my old friend, the energy norm error, I can see that there's a lot of energy norm on these sections, and that's because I ran them as solids. Now, this is a good example I like to show this because you can't use shells for everything here. So if I go to my shell version, and I now look at my mesh, so I've solved this as a shell, this is a shell, this, but not this. Does anyone want to take a guess as to why? I kind of hinted at it when I talked about those holes. Those holes that this plug is plugged into make it so you cannot use that as a shell because those make it so it's not equal cross-section. If you were to make that just a 2D shape, the holes would go away and you wouldn't know what they're doing. So that's the limitation. I got to run that as a solid. But it's no big deal because it's relatively thick. And also, this part, the mesh looks like total garbage because it's so complicated a shape. But I don't really need to worry about that so much because if I go to my displacements, look how far away that part is from my loads and my displacements over here. It's significantly far away enough that I don't really need to care about what that displacement is doing so much. I might want to enhance it later, but my main concern is the pipe itself because that's what's moving the most. And yes, that part, if I apply heat to it, is changing the overall stiffness of it. But you do have an advantage in that thermal studies and thermal calculations don't really need advanced meshing because they're just looking for one thing, temperature, and that's it. As opposed to looking for displacements and stresses, which are complicated three-dimensional vectors. So I don't really need to enhance that mesh in that area so much. In fact, what I really could do is replace that component entirely if I were to just measure how much force or displacement, if I were to just like probe right here and probe either the displacement or probe the force, then I could just replace that. Remember Jedi mind trick? And get rid of it. So you can at any time do that with any of the components that are causing you trouble. And it still is going to be just as accurate. All right, last example right here, we have a nonlinear cam example. I like to show this off because a lot of people have the connotation in their head that simulations are all static and nothing moves. But you can actually do some pretty complicated movement as long as you have nonlinear on your side. So in this case, what I'm going to do is simulate the action of a cam by using a nonlinear. So I have this cam on top, and I want it to rotate. The objective is to make sure that cam pushes on that electrical connection and breaks the circuit. So I want them to touch each other. So I've set up this nonlinear right here, and I have no penetration contact between the cam and the electrical connection. I have a fixture on the electrical connection, and I have reference geometry for rotation on the cam itself. And that's really it. It's not too complicated to set up. So now let me go to my solved version here. Oh, you're kidding me. Well, I think I have that video. Nope, not going to run for me. Well, there is one advantage. If I run this now, nonlinear simulation actually will run while, or show you results while you're running it. So I can just run this live. Look how brave I am, running nonlinear simulations live. Who else can do that, I ask you? So you can see as this runs right here, it pushes down and breaks my circuit. Now, notice that it didn't slow down when it broke that circuit. The reason is I didn't put in a no penetration condition between it. And you know why? The reason is I don't care. I just want that electrical connection to be broken, and that's it. I don't care what the force is. I can do that later. My question is yes or no, when I rotate this cam, does it give me the appropriate displacement? And the answer is yes. So later on, like I said, Rome's not built in a day. I can do a simulation where I do have contact to make sure that electrical connection is not going to break because of the force. But until then, I can just run it like this and see that I got the appropriate response. So this is a good example of using nonlinear to show dynamic bodies. I think a lot of people would expect you'd have to run this in motion, but you can't because motion can't show deformation of bodies. They can only do static kinematics, rigid body motion. So if you ever have to show something that's moving and displacing a body, then you got to go into your nonlinear. But it's not that it's impossible. It is there. Okay. Finally through that technical nightmare. I'll take any questions now, but ultimately what I want to express with this presentation is that you've got to think of finite element analysis as a process, and all processes have rules, and obviously they also have unforeseen obstacles. It's not that those obstacles are insurmountable as long as you use these tools and always use scientific method. That's really what I want to stress here. When you find a response in simulation, it's not that it's coming out of nowhere and it's magic. There's a reason why you're getting it. And those errors that come up in simulation, I know a lot of you probably think they sound like complete gobbledygook, but you and simulation are on the same side. You're trying to help each other. So those simulation errors are giving you information. And if you ever want more information, just contact your VAR. I mean, they all have a simulation engineer, and they're there to help you. And so these tools and others are here to help you, the user, to try to get through your simulations. All right, I'll take any additional questions, comments. I got business cards up front, and I'm legally obligated to tell you to take the survey, so take that survey. Thank you very much.